This video contains the solutions to sample exam number 2. So for the first couple of questions, we're looking at this table of values where we're given values of f, f prime, g, and g prime when x equals 1, 2, or 3. But part A only asks about f. It says find the equation of the tangent line to y equals f of x at x equals 3. So remember that when we're looking for an equation of a tangent line, we're going to be using our point-slope form of the equation of a line, which is y minus y0 equals m times x minus x0. The x0, that's the x value that they gave us. That's this 3. Now the y0, that's just going to be f of 3, which I can look in my table and see that f of 3, that's negative 4. And then what about the m? Well, the m is going to be the slope of my function at x equals 3. That's going to be negative 2, so that's what I'm going to put in here for this m. And then the only thing I have to do is actually plug in those values. So I get y minus negative 4 equals negative 2 times x minus 3. Do a little bit of algebra. Y plus 4 equals negative 2 plus 6. Subtract 4 from both sides. Y equals negative 2x plus 2. So that's the tangent line that I'm looking for. For part B, we're given p of x is f of x times g of x, and we're asked to use the product rule to compute p prime of 2. Well, the product rule would tell us that p prime of x is the derivative of the first function, f prime of x, times the second function, times g of x, plus the first function, g of x, times g prime of x. And now all we have to do is plug in 2. So p prime of 2, that's going to be f prime of 2 times g of 2 plus f of 2 times g prime of 2, and we can find all of those values in our table. Those are all going to be in the column corresponding to x equals 2. So we see f prime of 2, that's going to be negative 1, g of 2, that's negative 3, f of 2, that's 0, and g prime of 2, that's positive 1. So our derivative of our product function is negative 1 times negative 3 plus 0 times 1. That works out to be positive 3. All right, so this problem has to do with interpreting the values of functions and derivatives. So in this case, we're told that a restaurant, when they charge X dollars for a particular menu item, sells S of X items. So the way that you want to read these is you say, okay, well, what's S of 15, right? What does that represent? Well, the problem tells us that something is given by S of X. What is that? The number of items that they sell. So that means that this 30, that is S of 15. So that's telling me they sell 30 items. Because S of X represents how many items they sell, so S of 15 represents how many items they sell. Now, what does the X represent? Well, that's the earlier part of the statement here. So when they charge X dollars for a particular menu item. So if I'm saying S of 15, that's S of X, the X is 15. And so that means they charge $15 for the item. And now all I have to do is take those two little bits of information and put them together in a sentence. So I can say it a bunch of different ways, but my sentence, as long as it includes those two pieces of information, is going to be correct. So all I need to say is, when the restaurant charges $15 for the item, they sell 30 items. Now here we're given a derivative statement, but the x is still going to be 15. The x is still going to be the number in the parentheses, which means they're still charging $15. Now s prime, that's going to be the change in s divided by the change in x. So delta s divided by delta x, they're telling me this is negative 2. The delta s, that's items. That's the number of items that they're selling. And delta x, that's dollars. So this is going to be negative 2 items on the top divided by dollars on the bottom. So that's telling me the rate at which the number of items that they're selling is changing. So I'm going to start my sentence the same way. When the restaurant charges $15 per item, what's happening? Well, the number of items that they sell is decreasing. That's what that negative sign is telling me, is decreasing at a rate of 2 items per dollar. So in other words, every time they increase the price of the item by $1, the number of items they sell is going to go down by 2. So if the X goes up by 1, the S is going to go down by 2. Notice that because I said the word decreasing here, I put the number 2, not the number -2. The word decreasing includes the negative aspect of that slope. The fact that this number of items that we're selling is going down is indicated by the word decreasing. And that's really sort of a better way to explain it anyway. All right, so now we're going to use these two statements to predict a value in the future. And the way we want to think about this is we can think about it graphically. So if this is my X and this is my S, so remember X is the price and S is the sales, what we already know is that when X is 15, my sales are 30. So that means that on this mysterious graph, we've got the point 15, 30. But we also know that the slope is -2. So if I were to go to 16, my price goes up by 1, which means my sales go down by 2. So this is going to be +1, but that's going to be -2. And if I go to 17, it's going to go over 1 and down 2 again. And if I go to 18, it's going to go over 1 and down 2 again. Since I'm going down by 2 3 different times, that means my S of 18 is going to be approximately, I don't know if this rate of change is going to continue, but as far as I know, if we're just given the information that they're telling us, S of 18 is going to be approximately 24. So if the restaurant charges $18 for this item, now they're only going to sell 24. So that's the basic idea. We're given the slope information and we can use that to predict other values of this function. All right, now for these next several problems, we're just using our derivative rules and just finding a derivative. Remember, for these, you don't need to simplify, just step by step, be methodical, use the rules, and you should be okay. So we've got a quotient rule here. So we've got our top function, which maybe we'll call f, our bottom function, which we'll call g. And so my derivative here is going to be, think about having 5 different spaces, as we've talked about in class. And then on the bottom, we've got something squared. So this is going to be f here, f prime, sorry, here, f here, g here, g prime here, and g on the bottom. So remember, 3 of those 5 spots are just copy and paste. So 8x plus 1 goes here, f, that's going to be 4x squared minus x, and g, that's going to be 8x plus 1 again. So those are ones I don't have to think super hard about. And then f prime, the derivative of 4x squared, the 4 is a constant multiple, the derivative of x squared is 2x, and the derivative of x is 1. And then for g prime, the derivative of 8x is just 8, and the derivative of 1 is 0. So that's just going to be 8. And again, just leave it like that. Don't worry about simplifying, just leave it in that form. All right, this time we have a chain rule. If we think of this function as being a function inside a function, 6x cubed plus 8x minus 10 to the 5th, we can think of that as y equals u to the 5th. And then the u is going to be all that inside stuff, 6x cubed plus 8x minus 10. And so my derivative is going to be the derivative of the outside function, the derivative of u to the 5th, multiplied by the derivative of the inside stuff, u prime. Well, the derivative of u to the 5th, that's 5u to the 4th. And the derivative of u here, well, the derivative of 6x cubed, that's going to be 6 times 3x squared. The derivative of 8x is 8, and the derivative of 10 is 0. But remember, we've got to give our answer without the u in it, because u was a variable that we invented. So we've got to put back in what u was, so 6x cubed plus 8x minus 10 to the 4th power, and then multiplied by 6 times 3 is 18, x cubed plus, sorry, that should be x squared. I misread my own handwriting there, x squared, and then 8. So that would be what we would be looking for our final answer on that one. All right, another chain rule here. So we think of inverse sine of 4x. We want to think of that as the inverse sine of u. And we know that the derivative of the inverse sine of u is going to be 1 divided by the square root of 1 minus u squared. So that's 4x squared. And then multiplied by the derivative of 4x, which is 4. So again, I've got a chain rule. That's my derivative of my outside function. That's the inverse sine of u derivative, which is 1 over the square root of 1 minus u squared. And that's my u prime. So this time we've got to know the formula for the derivative of a log of a base that's not e. Remember, we know that the derivative of the natural log of x, that's just 1 over x. But if it's a log of a different base, the derivative of the log base 5 of x in this case, that's going to be 1 divided by x times the natural log of 5. So we're going to need to know that, but before we get to that, this is a product. There's a multiplication symbol between x and the log base 5 of x, and so this is going to require the product rule. Remember, draw your 4 spaces. This is going to be the first function, the derivative of the first function, which is 1, multiplied by the second function, which is the log base 5 of x, plus the first function, multiplied by the derivative of the second function, which is 1 over x ln 5. And again, we could clean that up, but we can just leave it like this. Don't need to simplify, just leave it like that. All right, finally, one more chain rule. We've got the tangent of 5t. Think of that as the tangent of u, and we know that the derivative of the tangent of u is secant squared of u, so this is going to be secant squared of 5t multiplied by the derivative of 5t, which is 5. So again, that's my derivative of tan u, which is secant squared of u, and that's my u prime. So again, I'm using the chain rule to figure that one out. Okay, so this time we're given a function, and we're told that this function represents the population of a city t years after 1950, modeled by this formula. And we want to find the average growth rate of the city from 1950 to 2000. So whenever you see that word average, we're not going to be taking a derivative here. Remember, an average rate of change is just a slope. It's just a change in y over change in x. So in this case, 1950, that's t equals 0, because t is the number of years after 1950. 2000, that's going to be t equals 50. 2000 minus 1950 is 50, so that's 50 years later. So this is just going to be p of 50 minus p of 0 divided by 50 minus 0. So I'm going to figure out what those two p values are. P of 0, that's going to be negative 1.7 times 0 cubed plus 72 times 0 squared plus 7200 times 0 plus 80,000. That's going to be a whole bunch of zeros. That's just going to give me 80,000. And then P of 50, very similar. I'm just going to put in 50 for my t. 50 cubed plus 72 times 50 squared plus 7200 times 50 plus that 80,000. Hop over to my calculator and work all that out, and I get 407,500, 407,500. So this is going to work out to be 407,500 minus 80,000, all divided by 50 minus 0 is 50. So that's 327,500 divided by 50, and that works out to be 6,550. All right, what are the units here? So the population, that's number of people, that's my y value. That's my top of my fraction. So this is going to be people divided by something. And then the numbers on the bottom, the 50 and the 0, those were years. So this is going to be people per year. So if you're struggling to figure out the units for a rate of change like this, just think about what were the units for the numbers on the top, what were the units for the numbers on the bottom. Okay, so for part B, we have this instantaneous growth rate. And again, I don't have to say that word instantaneous. If I just say growth rate, what I mean is the instantaneous growth rate. But in this case, since we see that word instantaneous, it's for sure going to be the derivative. So we're going to want what's the derivative at the year 2010. So first we need to find a formula for the derivative. So p prime of t, again using our power rule and our sum rule and our constant multiple rule, we're going to get negative 1.7 times 3t squared plus 72 times 2t plus 7200 times 1, and then the derivative of 80,000 is 0. Clean that up a little bit, I get negative 5.1 t squared plus 144t plus 7200. Don't need to simplify it, but it does make typing this stuff into our calculator a little bit easier. All right, what are we typing into our calculator? Well, 2010, how many years after 1950 is that? If I subtract, I get 60, so that means that 2010 is when t equals 60. So p prime of 60, that's going to be negative 5.1 times 60 squared plus 144 times 60 plus 7200. And again, working that all out in my calculator, I get negative 2520, and the units will again be people per year. So that's that one. All right, this time we've got an implicitly defined curve. So we have a function that's not solved for y, but we still want dy dx anyway. So what we're going to use is implicit differentiation. So we're going to take the derivative of both sides with respect to x. With respect to x. And what that means is, anytime we see something that just has x's in it, the derivative is going to look pretty normal. But anytime we take the derivative of something that has y's in it, we're going to have to be careful. We're thinking of y as being a function, even if we don't have our equation solved for y. So when we look at cosine of y, it looks very innocent, but when we take the derivative of cosine of y, we need the chain rule. So the chain rule says you take the derivative of the outside function. The derivative of cosine y is negative sine of y. But then, remember that's only half of the chain rule, then I have to multiply by the derivative of the inside function. The inside function was y, and the derivative of y is dy dx. On the right-hand side, the derivative of x squared, that's normal, that's just 2x. But the derivative of y squared, again, I need the chain rule. So I think of that as some function squared. So the chain rule says you take the derivative just as though it were a simple variable. You take the derivative of y squared and you get 2y, but then the second half of the chain rule says that you have to multiply by the derivative of the inside function. The inside function was y, and the derivative of y is dy dx. So now the calculus is over. Now all I have to do is some algebra to get dy dx by itself. So I'm going to move all the terms that have dy dx to my left-hand side. I've got sine of y dy dx minus 2y dy dx equals 2x. I'm going to factor out the dy dx. We get negative sine y minus 2y. And then I'm going to divide both sides by that minus sine y minus 2y. So I get dy dx equals 2x divided by negative sine of y minus 2y. And even though that formula has x's and y's in it, that's the best I can do to figure out what my derivative is. All right, now this time we've got a function raised to a power that's also a function. And the problem here is that our exponential rule and our power rule, neither of them are going to work here, because the power rule requires the power to be a constant, and the exponential rules require the base to be a constant. This time, neither one of them is a constant. So the way we're going to think about this is with logarithmic differentiation. So we're going to write this as y equals cosine of x raised to the sine x. And then we're going to take the natural log of both sides. So the natural log of y equals the natural log of cosine of x raised to the sine x. And the reason why we're doing that is that logs have this nice property that when you have an exponential term inside your logarithm, that power is going to come down. Now that power coming down, don't confuse that with the power rule, right? That's just a property of logarithms. So this is natural log of y equals the sine of x multiplied by the natural log of the cosine of x. Now I'm going to take the derivative of both sides, right? None of the stuff that I did up until this point was derivatives. I took the log of both sides and then I used a log rule. So now I'm going to take the derivative implicitly with respect to x. On the left-hand side, I'm using the chain rule. The derivative of natural log of y is 1 over y, multiplied by the derivative of my inside function. My inside function was y, so my derivative of y is dy dx. On the right-hand side, I'm using the product rule. So it's the derivative of the first function, multiplied by the second function, plus the first function, multiplied by the derivative of the second function. The second function is natural log of cosine of x, so there I'm using the chain rule. It's going to be 1 divided by the cosine of x, multiplied by the derivative of cosine x, which is minus sine x. So now dy dx, if I multiply both sides by y, is going to be y times all that stuff. So cosine x times the natural log of cosine x, plus that's going to be actually minus because of that minus sign. So minus sine squared x divided by cosine x. And then what I really should do is replace the y with what it actually is. This was my original function, so that's my y. So this is cosine x to the sine x times all that stuff. So cosine x times the natural log of cosine x minus sine squared x divided by cosine x. So there's my derivative. So a little bit complicated, but again, the basic procedure is You call your function y, you take the log of both sides, use implicit differentiation, and then solve for your derivative. Okay, so here we have a related rates problem. So we're told that a circular oil slick is growing in such a way that its area is increasing at a rate of 20 square meters per minute, and we want to find the rate at which the radius is changing. So I'm just going to draw myself a little circle here so I have a little visual. So what are we talking about here? Well, we're talking about the connection between the area of a circle and the radius of that circle. And that's a formula that we hopefully know, which is the area is equal to pi r squared. We're also told that the area is increasing at a rate of 20 square meters. So they're telling us that dA dt is 20 square meters per minute. And we want to find the rate at which the radius is increasing. So they're asking us for dr dt. dr dt equals question mark when the radius is 40 meters. So they're giving us one of the rates for our variables. We're asked for the other rate for our other variable. So that means we're going to use the related rates process, which is to take the derivative of both sides of our equation, not with respect to a, not with respect to r, but with respect to t. So if I start with a equals pi r squared, and I take the derivative of both sides, on the left-hand side I get dA dt. On the right-hand side, the pi is a constant multiple. And then for r squared, I need to use the chain rule. So r, we're thinking, is this function of t. So when we take the derivative of r squared, we get 2r to the first, but then we have to multiply by the derivative of our inside function. The inside function is r, and the derivative of r is dr dt. Now, we know a lot of these numbers. dA dt, they told us that was 20. R, they're telling us that's 40. dr dt, that's what we're looking for, so now we can solve. So this gives us 20 equals pi times 2 times 40 times dr dt. That gives us dr dt equals 20 divided by pi times 2 times 20, that's 80 pi, and that works out to be 1 divided by 4 pi. And the units here would be meters per minute. So that's my exact answer. And then as an approximate answer, I plug 1 divided by 4 pi into my calculator, and that works out to be about 0.08. Make sure you put the 4 pi in parentheses, and that's going to give me meters per minute. So in this problem, I asked for an exact answer and an approximate answer, so those are my two answers there. All right, last up, we've got this graphical interpretation question. So we've got this graph of f of x, and the first thing I'm asking for is f of 0. Don't get tricked by this problem. It's hopefully an easy problem because all I'm asking for is what do you get when you plug in 0? So if I look at 0 on my x-axis and I plug in my function, I get 3. That's just asking for the y value for the function, so don't think it's more complicated than that. Now f prime of 0, that's asking for a slope. But because what we can see here is that my function is made out of some straight line segments, I can just count boxes to figure out what the slope of my tangent line is, rise over run. So from this point, I can go up 2 squares and over 1, so my rise is +2 and my run is +1, and that works over here as well. My run is +1, my rise is +2, so my slope here is going to be change in y over change in x, which is going to be 2 divided by 1, also known as 2. And then finally, f prime of 1. So if we look at x equals 1, that's this point here. And since I see a sharp corner, or what we called a cusp, on my function, that means that my f prime of 1, that's undefined. So our slope is not defined at any sharp corner like that. Because from the left, the slope is one number. From the right, the slope is a different number. So we get this kind of inconsistency. And we know that in that case, the limit doesn't exist. So that's the exam. Again, a lot of different stuff that we've talked about from chapter 3. Just make sure that you're up on all the derivative rules. You've got all those memorized, the different concepts, the techniques like implicit differentiation we use several different times. So it's a lot of stuff to keep track of, but keep studying. Let me know if you have any questions, and good luck.